The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and thank you for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is oxygen measurement for inerting. This topic is being presented by Ken Solon from Baker Hughes, a GE company. Ken is a regional sales manager for moisture and gas instrumentation at Baker Hughes Panametrics Measurement and Controls Group. Previously, he has been the product manager for TD-LAS, moisture trace, moisture analyzers, and humidity test and calibration instruments at GE. He has been with the organization since 1999. He's worked as a sales engineer and business manager in the field of industrial sensors, instrumentation, and process controls for 31 years. He also spent 5 years as an analytical chemist, primarily working with gas chromatographs for EPA protocol testing. Ken has an AS degree in chemistry from Kingsborough College in Brooklyn. He is an instructor for the humidity measurement and calibration tutorials for the NCSL, which is the National Conference of Standards Laboratories, MSC, which is the Measurement Science Conference, and process measurement classes for ISHM, which is International School of Hydrocarbon Measurement, and AGMSC, which is Appalachian Gas Measurement Short Course. Ken is also a member of ISA, which is International Society of Automation, and AGA, American Gas Association, and SGA, Southern Gas Association. He certainly has a lot of credentials there. We expect the presentation today to last roughly 30 minutes, and then we will open it up for question and answers. During any time during the presentation, you can send your questions through the question box, which is in the right side in your webinar controls. I also want to mention that the webinar is being recorded. You'll each receive a follow-up with an email and a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Ken.
Well, thank you, Nicole, and thank Transcat for hosting this webinar. Today's subject is oxygen measurement for inerting. And oxygen is an essential gas on planet Earth for life. If you think about plant matter, they take in CO2 and output O2, oxygen. And we, of course, breathe oxygen. We need oxygen for life. But oxygen has the property of driving corrosive reactions, and it also is an essential ingredient for combustion. If we think about our automobiles, the way it runs is fuel is injected or carburized into our manifold, and that's mixed with air, which contains oxygen, and as that combusts, if we have efficient combustion, we get CO2, heat energy, and water vapor. And the human body is a type of engine. We do breathe in oxygen. Our fuel is mainly carbohydrates and fats and so forth, and those are oxidized or combust in a way. And our byproduct when we breathe out is CO2, water vapor, and we're constantly generating energy to work our bodies, let's say. But there are many applications where excessive oxygen can be a hazard. And in particular, whenever we're storing fuel or solvents or flammable liquids, typically these are stored in a tank. And it takes three things to have a combustion or a fire. We need a fuel, we need oxygen, and we need a heat or an ignition source. So commonly known as the oxidation triangle or the combustion triangle. And if we take away any of the legs of the triangle, we can't support combustion. So what's done in industry and in the chemical and petrochemical industry is the headspace above the liquid is purged with an inert gas. And we want to limit the oxygen typically to 4 to 8%. If we get the oxygen down to that level, we can't support combustion. Now, ambient air, the air that we breathe, contains about 21% oxygen. So as you empty the tank, as liquid flows out the tank, you create a vacuum, and the tank naturally wants to suck in ambient air, and with that ambient air, you're bringing in oxygen. So there are two ways to monitor a tank. You can do it by pressure, or you can do it by oxygen measurement. With pressure, it's a good measurement, but it doesn't measure the oxygen content. So what's typically done is you measure the oxygen content of the headspace, and you have a feedback control to limit the oxygen to the 4 to 8% value. The way we measure oxygen, or I should say one of the ways that we measure oxygen, is through its property of paramagnetism. And paramagnetic basically means that oxygen is drawn to a magnet. And in the picture, we show a very strong magnet, and we've poured liquid oxygen through the poles of the magnet. And you can see that there's sort of a fog suspended between the poles. That fog is actually liquid oxygen suspended because it's drawn to the magnet. Cold oxygen has more of an attraction to the magnet than warm oxygen. So as the oxygen warms up, it loses some of that attraction to the magnetic field. In the sensor we construct, what we have is a strong magnet, and we have an orifice that controls the flow rate through our measurement cell. In our measurement cell, we have two sets of thermistors that essentially act as small heaters. And we also control the temperature of that cell to a pretty accurate value. We're controlling to 45 degrees C, or 60 is about 122 degrees F, or 140 F if it's 60 degrees C. And as the gas or the oxygen is drawn to the magnet, as it passes across the heated thermistor, it loses some of that attraction, and that causes a differential pressure. We get a differential pressure, and another name for differential pressure is wind. And that wind, as it were, just like you can feel cooler if you're in front of a fan by having that fan blow across you, or on a winter's day, you feel a lot colder when the wind is blowing via the wind chill factor. We get a cooling effect. So the difference between the wind generating thermistor, sort of showed there in black, and the wind receiving thermistor shown there in red, is measured as a resistance, and we put that in a bridge circuit, and the output signal is then directly proportional to the concentration of oxygen. Now, one advantage of this thermoparamagnetic sensor is it has no moving parts. So it can be made very rugged and used in a lot of industrial applications. This is just a picture of the XMO2, which is the Thermoparamagnetic Transmitter. It provides a linear 4 to 20 milliamp signal. It does have a digital interface as well as the analog 4 to 20 milliamp signal. You can also get it in a rack mount version for safer area applications. This unit here, as pictured in the sort of the upper section, is the explosion-proof version, and that measures the full range of virtually 0 to 100% oxygen. Now, typically when we use these in inerting, we like to calibrate them at roughly 2 times or the span of the area of interest that we're measuring. So if we're measuring 4 to 5%, we'd like to calibrate them at 10%. But even in that application, you can actually calibrate these to ambient air at 21% if you have a flowing source of ambient air. So there are a number of applications in addition to the inerting. We also measure oxygen purity in the manufacture of olefins, which is ethylene is the main one, and is the precursor for polyethylene, and that makes a lot of plastics and synthetic materials. In landfill or biogas, of course, again, like any fuel, natural gas, you can't burn gas unless you have oxygen present. So in the storage and compression they want that gas to be oxygen-free. In ozone production, ozone is being used today as a substitute for chlorine. It has many of the same kind of disinfectant and bleaching properties. We use these for flare gas applications, in reactor feed gases. In wastewater, when you're trying to break down sewage or waste, there are two methods. One is anaerobic digestion and the other is aerobic digestion. Anaerobic means without oxygen and aerobic means with oxygen. So you would be enriching that waste product with oxygen to help the microbes eat up the waste in the aerobic. And in solvent recovery, that's another application. Of course, the solvent vapors in the presence of oxygen is a flammable or explosive hazard. Of course, we don't normally put our sensor directly in the headspace of the vessel. We normally draw a sample out. By drawing the sample out, we can condition it, we can adjust the flow rate. In this particular assembly, which is one of our standard ones for inerting, we have a trap which traps liquids. So as we sample via a vacuum pump, we go through a coil to adjust the temperature or condition the temperature, and any liquid falls into the trap. And then we have a filter flowing a gas into our analyzer. This assembly or sample system also has our zero and span gas input. So for example, we can use nitrogen as our zero gas, and we could use compressed air, which contains 21%, as our span gas for calibrating these units in the field. And the next slide is really just showing that we can hook in our transmitter, the XMO2, to a display unit. That display unit has relays, so you can semi-automate the calibration process. You can also calibrate these by internal push buttons in the enclosure of the XMO2, or by connecting it to the digital telemetry. We do have a software package called IDM, where you get the telemetry on your computer and you can send commands back to do the zero and span calibration of the XMO2. This graph is also just showing some trending information where we had a step change from 21%. We switched in nitrogen, and you can see that it travels downward, reduces its reading until we're at virtually 0% on the nitrogen feed or the calibration. One of the big areas that we're involved with is on tankers that are seaborne, fuel tankers, and they produce inert gas on board. They use the product of combustion. So one of the products of combustion, of course, is CO2, and CO2 won't burn. So they clean up that CO2, they use cooling to condense out any liquids, and they clean it up, actually use seawater for cooling. And then they feed that product of combustion gas to the headspace of the interior tankers. So there are thousands of these deployed globally on tankers. You can actually see the XMO2 here with our display unit down in the corner. In a similar fashion, there are lots of reactions, like in making plastic resins. When we make polycarbonates and other plastics, some of the precursor material, those reactions occur in vessels where they don't want rapid oxidation. So again, they want to limit the oxygen. And in this case, we built a sample system that also includes explosion-proof solenoid valves to automate the calibration process. So from the customer's PLC, they can initiate the calibration process remotely and on demand. In vapor recovery systems, and we all experience this when we fill up our automobiles in the olden days before the gas pumps had a vapor recovery nozzle on a hot summer day, you could actually see the gasoline vapor escaping from the nozzle, or when you were filling your automobile. Those back in the days when you used to fill the gas from the rear of the car and fold down the license plate and so forth. Today you have an extra nozzle that recovers that vapor, and the vapor is much more dangerous in terms of an explosion hazard than the liquid. I've never tried this, but they say you can throw a match in liquid gasoline and it won't explode, or it won't go on fire. It actually will put the match out. And I believe there's actually some YouTube videos that show that, but I wouldn't recommend trying that at home. It's really the vapor that has the most danger. So again, what we're doing is limiting the amount of oxygen in the vapor so that you cannot support combustion. And these are just some other projects that we've been involved in. Some of them are quite involved. We may have multiple units. They may be out in remote locations, like out to sea on a floating platform. These floating platforms are like floating refineries, essentially. So there we just see a picture of a turnkey system for the floating platform. One of the most widely produced chemicals is thermoparamagnetic acid. It's a commodity chemical, and its big application is the precursor to PET. PET is the plastic that we use in water bottles. And as you all know, water bottles are proliferated globally. Probably the cap on a water bottle will cost more than the water that's in it, but it's a good way of having a sort of a sanitary, clean bottle of water by having individually packaged bottles. So here again, we see a technician feeding the unit with a zero or span gas as a routine maintenance thing. We recommend calibrating it every 3 months or so. Another technology that we offer is the galvanic fuel cell, and this uses a lead anode sealed in a sealed cell, and inside that cell is an electrolyte. The electrolyte that we mainly use is potassium hydroxide. So this is not unlike a battery. As the lead combines with oxygen, it releases electrons, and we measure that in terms of current. It's a very small current coming out of the cell, measured in the microamps. So this device will then amplify that up to the milliamp level as a signal. There's also a local display. Now this sensor does deplete over time. The higher the oxygen concentration you expose it to, the faster it depletes. It has so many percent oxygen hours. So if you expose it to 21%, which is ambient air, it would deplete 5 times faster than if you expose it to 100%, or I should say that the other way around. If you expose it to 100%, it would deplete 5 times faster than if you expose it to 21%. But still, it's a very good sensor. You can calibrate it to ambient air for 21%, and we also have sensors that are down in very trace levels of oxygen, ppm levels. Now, sometimes we don't think about inerting other than in chemical fuel tanks, but there are lots of industrial applications in just ambient air and ingress monitoring. In glove boxes, these are just microenvironments, sometimes called isolators, where certain functions go on. It could be for pharmaceutical compounding. It could be for working with nuclear fuel. It could be with working with microelectronics, where we want the environment to be pretty much devoid of oxygen. The same in food and pharmaceutical processing. You can store tablets under an inert gas, and they'll last longer than if they're exposed to oxygen, certain tablets. And likewise in food products, certain food products will spoil faster when they're exposed to oxygen as compared to an inert gas. when we're doing welding, we also have a shield gas, which protects the weld. So that shield gas covers the weld. It's usually argon, helium, or nitrogen. And the same principle occurs in metal processing. There's a number of annealing and heat treating processes where we want to be devoid of oxygen. We want to limit the oxygen concentration to get the properties in the metal that we want. So this slide is just showing a simple sampling system for the OXY.IQ that uses the galvanic fuel cell. We're just flowing through at a control rate. We do have a pressure regulator because these measurements are made at atmospheric pressure. And we have a little filter in line to interdict any particulate or any oil mist that might be present in the sample. So this unit would then put out a linear 4 to 20 milliamp signal. And here at GE, Baker Hughes, we can customize these sampling systems as well per the specific application. So as I mentioned, welding, particularly in TIG and MIG welding, and today a lot of the welding is done through robotic welding, robotic arms. So at the tip of the weld tip, that is flushed with an inert gas, usually argon or nitrogen, to protect the weld from oxidizing rapidly while it's hot, so to speak. In the manufacture of contact lenses, these are done in oxygen-deprived environments or low oxygen environments. These facilities are under strict FDA regulations, so they have very strict quality control for the environmental conditions, and sensors have to be calibrated on a regular basis. In making the individual coffee pods or packets, these are also packaged under nitrogen blanket. This particular firm was using lots of nitrogen. They installed one of our sensors, and they feed back the signal so that they only supply the nitrogen on demand, and to keep it to roughly about 4% oxygen. And by doing that, they were able to realize a lot of savings in the consumption of nitrogen. It's a on-demand purge versus just fully purging the packaging line with nitrogen 24/7, as these machines run 24 hours a day, 7 days a week. So as we sort of come to the end here, one of the considerations for using oxygen transmitters and sensors is to give your supplier pertinent information so that they can select the right system. And we have a convenient form for collecting that information. Either you can fill it out or we can fill it out with you over the phone. But we're trying to capture what the process and environmental parameters are, what the gas composition is, the temperature of both the process, the pressure of the process, as well as the ambient temperature, the electrical requirements, the safety requirements. Is this a hazardous area? Do we need Class 1, Div 1, or Div 2 certification? Sometimes we need to pull a vacuum to pull the sample. Do we have compressed air for running a aspirator to pull the vacuum, or can we use a vacuum pump? Are there any special requirements? And do you need a field startup and commissioning and training? We can send someone out to your facility to give you training on that and commissioning. So with that, I think we have a few minutes left, and we can certainly open it up for some questions.
Thanks, Ken. As Ken said, that's the conclusion for our presentation portion of the webinar. We'll now move on to the question and answer session. And as a reminder, if you'd like to submit a question, you can do so through the question box in your webinar controls, which is on the right panel. So let's go to our first question. How do you calibrate the oxygen analyzers in the field?
It's actually pretty simple. You do have to have a known gas. We use for the zero gas in a lot of applications, we just flow nitrogen through. We normally use a good source of nitrogen, liquid nitrogen, boil off. And with our system, you just have to hit a button and the unit calibrates itself to zero. You then switch over to the span gas and you flow that known amount of gas. Now, you would tell our analyzer what that value is. Again, just hit a button, either remotely from the software or from the unit itself, and it would calibrate itself to that known value. In this example here, we're calibrating to 21% as our span, which is the concentration of ambient air, and nitrogen for our zero gas.
Okay, for the OXY.IQ, how often does the sensor need to be replaced?
It's dependent on the concentration over time, but if you expose a percent sensor to 21%, which is ambient air, we get about 12 to 8 months lifetime out of that sensor. It also depends on temperature. In higher temperature applications, the cell depletes faster. It's akin to a battery.
Okay. What is the effect on changes in pressure on the oxygen transmitters?
That's a good question. In reality, our sensors react to the partial pressure of oxygen. And the partial pressure is directly proportional to the concentration. So the example I always give is that at sea level, we have 21% oxygen in the atmosphere, but on Mount Everest, we also have 21%, but you would have difficulty breathing because the total pressure is so much less than 1 atmosphere. I think we have about half an atmosphere on Mount Everest. So therefore, the partial pressure of water will only be half. So you do have to compensate for pressure, and that's why we standardize these measurements at atmospheric pressure.
Okay. What amount of flow is required for these oxygen analyzers?
The flow rate should be about 1 standard cubic feet per hour, which works out to about half a liter per minute. Just as for instance, if you put your finger on the outlet, you'll barely feel any flow there. It's a very small flow.
Okay. And can these sensors be used to measure dissolved oxygen in water or other liquids?
No, they're only for gas. And sometimes people also get a little confused with the word vapor. When we say vapor, we really mean something in the gas phase. But sometimes we think of vapor as being, like, for example, a cloud. When you look at a cloud, that's actually liquid water suspended in the air. It's fine droplets of liquid water suspended in the air. Most vapors and gases are invisible. So we're only measuring with these technologies in the gas phase.
Okay. All right, that looks like that's it for the questions, and that concludes our time for today. If you do have further questions that went unanswered, or you'd like to find out more about Transcat's product and service offerings, you can contact us at 800-800-5001 on the web at transcat.com, or you can email me directly at nvanwert@transcat.com or nicole.vanwert@transcat.com. I thank you for joining us today, and we hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Thanks, Ken.
Thank you. Okay, bye-bye now.
Bye, take care.